So now let's look at the next topic, nanoimprint lithography. So far we have talked about a light-based lithography that includes deep UV lithography, extreme UV lithography, and X-ray lithography, and the charged beam-based lithography that includes electron beam lithography and ion beam lithography. And now we will look at a mechanical force. We do lithography using mechanical force. What is the case? Which is the case for the nanoimprint lithography? The idea for the nanoimprint lithography is rather straightforward. There are two types of the nanoimprint lithographies. The first one is called a thermal imprint. The second one is called a UV Curie imprint. So for the thermal imprint, it is like a hot embossing process. So we have this yellow color. This yellow color is the resist. So we heat up the resist so it becomes soft. Then we press the mold onto the soft resist. Then we cool down, we separate. Then we can add away the residue layer. For the casing of the UV Curie resist, so we have a liquid resist. We have the liquid soft resist. As a result, so we can do the imprint at the room temperature without heating up. Then we shine the UV light. So we shine the UV light to cross-link, to harden the UV resist. Then we separate and we add away the residue layer. So usually, as you will see later on, there is also this purple color underlayer. This is called underlayer. So then we transfer the pattern into the underlayer. Then we can do the following process. So now we look at thermal imprint first. For the thermal imprint, so we need to heat up, hold it at high temperature, and then cool down. So when the temperature is reached, so we can apply the pressure. Then after some time, when the temperature is low enough, so we remove the pressure. So typically, the temperature is done at 100 to 200 degrees, about 30 to 50 degrees above the glass transition temperature of the polymer. So usually we use a thermoplastic or thermoset polymer. So for the pressure, it's typically 20 to 50 atmosphere pressure, or at least 10 atmosphere pressure. But this depends on the pattern design. For example, for the protruded patterns, we need a low pressure. So for the recessed pattern in the mold, we need a high pressure. So this is easy to understand. So the main advantage for the nanoimprint lithography is the very high resolution. As you can see here, this is why you have the 10 nanometer mold etched into the silicon. This is why 10 nanometer holes imprinted into the resist, which is the PLMA. So this is the PLMA polymer film. Then we do the metal deposition. We do the chromium deposition and the lift off. So we get 10 nanometer diameter metal dot. So this was done in around 1995. So at that time, the industry, the semiconductor industry, the feeder size is about 500 nanometer. So in the middle of the 1990s, the industry, they get down to 500 nanometer. But for nanoprint, it goes to 10 nanometer easily. So this is what very exciting in the 1990s. Another advantage for the imprint is we can do the 3D imprinting. For example, if we have a mold that have this two-layer or three-layer structure, then we can do the imprint to create two-layer or three-layer structures. But normally, if we do the same thing using optical lithography, you will need two lithography, two photomask, two lithography. But if you do by imprint, you need only one imprint, one mold, one imprint. So this can be used for the patterning the via and the inner connections. So we know that for the semiconductors, for the integrated circuit, so we have the via. The via is the holes make the vertical connection between different metal layers. Then we have the interconnection lines. That is the lines on each layer. So now let's look at the imprint resist. So it is not surprised that the most popular resist at the beginning is PLMA. For the casing of the PLMA resist, this is a thermoplastic polymer. At low temperature, it's glassy. Then you have the transition temperature become soft, more and more. So this is the viscosity. This is the temperature. At the even higher temperature, you get the viscosity gets much lower. It is very good for the flow. So normally when we do the nanoimprint, we do at this temperature range. If we go to higher temperature, it will also work. But usually we do at this temperature. So the only reason that we use PLMA, so the early work for the nanoimprint is all done using PLMA. The only reason for this is because this is available in the lab. We know that people use PLMA as the electron beam lithography resist. It's easily available, and the people are familiar with it, so they pick it. But actually, this polymer is not very good for the thermal imprint. So the glass transition temperature is 105 degrees. So we need normally higher than 150 degrees for the imprint. Secondly, this polymer have this chemical bond. So we have a carbon oxygen. So this is a very polar. It's very polar. So when we have the polar bond, you have very high surface energy. When we have high surface energy, the separation between the mold and the wafer will be difficult. So a better choice than PMA is the polystyrene. For the casing of the polystyrene, so we have only this is the polystyrene. So this is the polystyrene. For the casing of polystyrene, we have only carbon-hydrogen bond. It is less polar than PMA. So then it has lower surface energy, easy separation between the mold and the substrate. Yet better polymer, but this one, the TG is close to the PMA. If we want to do the imprint at lower temperature, you can use the polyvinyl phenyl ketone. This one, the property is comparable to the polystyrene, but TG is only 58 degrees, and you can do the imprint at below 100 degrees. So this one, the chemical structure is something like this. So here you have one carbon, oxygen, here. This one. So this is the polyvinyl phenyl ketone. So we know that normally we want to do imprint at a lower temperature. If we still want to use the PMA, but we want lower temperature. So how to lower the glass transition temperature of the polymer? So this can be done by adding the plasticizer. I'm sure you are familiar with it because you have already taken the polymer course. So when there is no plasticizer, it's so viscous. We add plasticizer, it becomes less viscous. If we add too much of it, it becomes like a liquid. So the plasticizer is monomers, solvent, or small molecules. They can be a liquid to make the flow much easier. So we know that when we have the lower glass transition temperature, we can do the imprint at a lower temperature, and also we get good polymer flow at the moderate temperature, and no problem, smaller problem for the thermal expansion and the shorter thermal cycle time. They are all good properties. But the problem, so when you have the TG is too low, for example, in this case, it's only 40 degrees. So this is the pattern after imprint. Then after 60 degrees for 5 minutes, you see the polymer, they reflow. There is the reflow of the polymer, so the pattern gets degraded. That means a too low TG is also a problem, because when we do the following processes, for example, if we do the metal evaporation, or if we do the polymer etching of the polymer resist, there will be some kind of heating. So this heating, it can also cause reflow. So then we have the contradiction. So we want lower imprint temperature, but also we want thermally stable imprint. So how to realize this? So this is realized by using the called a thermoset or thermocurable resist. So in this case, so the pre-polymer has low glass transition temperature, so we can do the imprint. At low temperature. So during the imprint process, so the TG goes up. So glass transition temperature goes up because it becomes cured, cross-linked, cured. It goes up. As a result, so after imprint, the pattern will be stable thermally. The pattern will not deform because of high temperature, because the TG is already very high after the imprint. So this is called the thermoset or thermal curing resist. So this one is developed by the company a German company called Micro Resist. If we use a thermal cure resist, so we can do the isothermal. It's called isothermal imprint. That means there will be no thermal cycle, no heating up, no cooling down. We do everything at the same temperature. So after imprint, you don't cool down. You just separate the mold from the wafer. So because we don't, there is no thermal cycle, so we can reduce thermal expansion. We can reduce the ACO of the thermal expansion. The imprint time will also be much shorter because we have no cooling. So normally the heating up takes very fast. The heating up can be very fast, but the cooling down takes time. So this is the starting material they have tried. This is why you can see for the pressure. So we need temperature 180 degree, 190 degree temperature, and time we need more than 1 hour. So this is not so good. High temperature, long time. So how to reduce the time and reduce the temperature? To reduce the temperature, as we have seen, we can add some plasticizer. So when we add a plasticizer, the glass transition temperature will be lower. Then we can do the imprint at 100 degree. To reduce the curing time, so we can add some thermal initiator. So this thermal initiator will help the curing cross-linking with the polymer. So after this, we get this imprint can be done within 10 minutes. So besides the regular thermoplastic polymer or thermoset polymer, so we can also add something into the polymer. For example, we can add some quantum dot. We incorporate quantum dot into the thermoplastic or thermoset resist. So here's the photo of the quantum dot. This is the fluorescent. This is the fluorescent image. So you can see you have the green color, red color. They are the same quantum dot, the CD, SE, the same quantum dot. So first, what is the quantum dot? So quantum dot first, we know it is the nanoparticle. It is nanoparticle. But if we have the gold nanoparticle is not quantum dot. So nanoparticle alone is not quantum dot. Then we have the second requirement, it has to be semiconducting. So when we have semiconducting nanoparticles, it is called a quantum dot. In this case, we use this CDSE. So this is the semiconductor of the 2,6 group. So we know we have the group 4 semiconductor like silicon and germanium. So when we have the 3 and 5, then the like gallium arsenide, then here is the 2,6 semiconductor. So we have this. So when we have different colors, so what make the color difference? So which one, the green color, red color, which one has the smaller particle size, nanoparticle size? So as you can imagine, so this green color has the smaller particle size. So because when we have this quantum confined effect. So when we have, if this is the energy barrier, you can see we have smaller feature sets. These are those are energy level in this barrier. When you have smaller feature sets, the energy level become higher. You get higher band gap. So that means smaller feature size, bigger nanoparticle size. So from this image, so this is the image, no illumination. This is the image with the fluorescent illumination. So usually this one is done by shining the blue light. So when you shine the blue light, you can have this kind of colors. The blue light has the photon energy higher than the green or red color. So when you see this, you may think about what is the application of the quantum dot. If you go to the Best Buy, you know we have something called QLED TV. This is the quantum dot light emitting diode TV. But in this case, so the quantum dot is just nanoparticles, but the quantum dot itself is not diode. So we don't use the quantum dot as a diode. So what do we do? It's different from the other one. It's called OLED. You can also buy OLED TV, or you can buy a QLED TV. But OLED TV, this is the organic light emitting diode. We use organic semiconducting materials. So this one, the organic material itself is used for the diode. But for this one, the quantum dot is only used for the backlight. We know that for the casing of the liquid crystal display. So liquid crystal display, this one we need the backlight, and we also need the filter. But when we use the quantum dot, when we use the quantum dot, so the backlight itself we have different colors. So the color is generated by the quantum dot. Then we do not need a filter, but we still need this liquid crystal display. This one is liquid crystal display, but with the quantum dot as the backlight. So we have different color of the quantum dot. So normally we shine the LED. So the LED itself, this one is blue. So we have the blue LED, so this gives you the blue color. But then when this blue color goes to this cosmos dot, so give you the green color. Green color. So when the blue color give you goes through this cosmos dot, give you the red color. So you have the RGB 3 colors. And that's useful for the commercially utilized for the TV. Now this is another polymer. This is the semiconducting polymer. The semiconducting polymer, those two of them, they are also thermoplastic polymer. As a result, we can do the imprint onto it. On the left side is the MEHPPV. So this is the chemical structure, a TG 65 degree, imprint 120 degree at the 20 atmosphere pressure. So on the right side is called a regio regular P3HC. This is also a semiconducting polymer, is also a thermoplastic polymer. This one, it has a very strong physical bond with high glass transition temperature. So we need higher temperature and higher pressure. So this is the color. This is the color of this MEHPPV. From this color, you can figure out what is the use of it. Why it appears red color. So it appears red color because the blue color light, it gets absorbed. The blue color light gets absorbed. So you leave behind the red color of the polymer. So this one can be used for the solar cell. So it's called a plastic solar cell. That means it's the solar cell using the semiconducting polymer. So the advantage for the plastic solar cell is flexible, lightweight, tunable electrical properties. So for the organic material, so we can play with the chemical structures. We can have different choices of the chemical structures to give you different electrical properties. But for the inorganic semiconductor, for example, silicon, the band gap cannot be tuned. So the fabrication of the plastic solar cell can also be very cheap. So if it's plastic, you can do like a roll-to-roll nanoimprint, like where you print newspapers. It is very efficient. But the problem for the plastic solar cell is the energy conversion efficiency. Energy conversion efficiency is low. So normally it is well below 10%. For the classical silicon solar cell, you get about 20% energy conversion. But for the polymer solar cell, you get about below 10% conversion efficiency. So how to improve this? This can be done by using the nano-patterning the pin junction. So how will this work? So for this case, this is a planar. This is the planar case. For the planar case, so you have for example, when you shine the light, you have electron and the hole. You generate electron and the hole. So then the electron hole, when they move around in this layer, it got recombined. Then it's not good. If they got recombined, it's not good. So normally, what do we want? So we want electron and the hole, they got separated. One goes to the P type, one goes to the N type. But in this case, they got recombined before they can go to the other, because they can go to the P set. So we have this interface. The P region and the N region, they are very close to each other. So that means the electron and the hole, they can go to this boundary layer. So once the electron hole go to this boundary layer, they get separated right away. Then electron go to one side, hole go to another side. Then you have the charge separation. So it is effective to generate electricity. So effectively, you reduce the distance between the P and N. So make the electron hole, they can go to the boundary, go to the junction area, then the charge gets separated because of the built-in electrical field. So now let's look at imprint for the large feature sets. So it's different from other lithography. For other lithography, it's difficult to make high resolution. But for the classical imprint, it's difficult to make low resolution. So small feature set is easy, large feature set is difficult. So this is opposite to other lithographies. So first, let's look at small feature sets. What is the limit for the small feature sets? So here you imagine that we press the liquid resist. So this set is the resist. This set is the mold. In this case, we have a cavity. So we have a cavity in the mold. So you press the substance, molten liquid resist into this cavity. How much pressure you need? This depends on the surface tension, surface energy, or surface tension. You can imagine the force, the surface tension force equal to gamma times the parameter 2 pi r divided by the area pi r squared. The force divided by the area, you get the pressure. The r cancel out, you get 2 gamma over r, you have 1 over r. That means the pressure is proportional to 1 over diameter. The smaller feature size is more difficult to imprint. But for the protruded patterns, we have pillars, and it will be much easier to do the imprint. You can have low pressure, you do the imprint. For example, in this case, you have the carbon nanotube. It's 2 nanometer. After imprint, you see the pattern into the resist, or even 2 nanometer pattern can be imprinted into the resist easily. But then the question is, what is the limit for the imprint? What is the resolution limit for the non-print lithography? Actually, there is no limit. As long as you can make the mold, you can do the imprint. But no limit for the mechanical imprint lithography, no limit for the resolution. So we know that for the optical lithography, the resolution is limited by the diffraction. For the electron beam or ion beam lithography, the resolution is limited by the scattering over the electron beams. But for the imprint, there's no limit. You can get even 1 nanometer or even smaller. So why is it hard to make large feature size? Because when we have large feature size, so we need more polymer to displace over longer distance, more polymer to move around over longer distance. This will take some time. So normally, to solve this problem, we can do a two-step process. So we do, for the small feature size, high resolution, we use imprint. For the large feature size, we use the optical lithography with the alignment. So below shows you the problem with the imprint that has both small and large feature size. You can see in the first example, for the first example, so the mold, this large feature size got stuck. In the end, the pattern head here and the pattern head here is different. For the second case, the mold gets bended. So the residual layer here, so the residual layer thickness is not uniform. For the third case, we have the small feature size surrounded by the large feature size. So the polymer cannot flow inside. As a result, you get this not uniform imprint. So now we want to see how large feature size we can get. So here we're using a simple model. So in this model, we assume a periodic mold structure. So we have the line, whole line, a trench, a line, a trench, line, trench. So we have line, trench, periodic mold structure, which appeared to be a 2L. So we ignore the initial force. Initial force is the MA term. So we assume we have the steady, we go to the steady flow very quickly. So we can ignore the initial force. Gravitational force is always small for this macro scale. The surface tension. So we know the surface tension is proportional to the surface tension. The effect of the surface tension is proportional to 1 over r, as you see here, 1 over r. We have larger feature size. When the r is very big, so this can also be ignored. So here we talk about the large feature size, so we can ignore the surface tension. So we also assume that the depth of the trench is the same as the resist thickness. So in that, we do some derivation. So we have the pressure. Applied from here. This pressure is the same as the pressure inside the resist, because the pressure is the same in the liquid. But this pressure here will push the resist to move this way. We push the resist to move to the right side. Then the flow between the two layers will be something. The flow will be something like this. This is the high flow speed and low flow speed. Then this flow can be calculated. In the end, you know how long it will take to fill in this trench. The formula given by L. This is the formula you get. So now let's look at whether this formula makes sense or not. R equal to H0. So you can see the thicker the resist, the easier to make large feature size. This makes sense because thicker the resist, easier for the flow easier for the flow. The higher the pressure, the longer the imprinting time. The tau is the imprinting time. Higher pressure, longer time give you larger feature size. This also makes sense. So the lower the viscosity, also the lower the viscosity also give you larger feature size. The mu is the viscosity, so this also makes sense. So now let's look at what we can do here. So we have this formula here. We have this formula here, the P tau over mu. So we don't want to use too high pressure. So too high pressure may break the mold. Too long time is also not very good. So what we can do, we can have lower viscosity. So now let's look at how to reduce the viscosity. For the case of the pyramid, for the case of pyramid, so the viscosity will depend on the temperature. Obviously, the higher the temperature, the smaller the viscosity. You can see the higher the temperature, the smaller the viscosity. It also depends on the molecular weight. So the higher the molecular weight, the higher the viscosity. In the end, we get a formula like this. Log mu is the viscosity, and log molecular. This is the molecular weight. This is the temperature term. Tg is the glass transition temperature plus the constant. So here we have this number n. So for the molecular weight, MW smaller than MC, which is 30 kilogram per mole, n equals to 1. This is unentangled molecules. But when the molecular weight is higher than 30 kilogram per mole, n equals to 3.4. It is entangled molecules. So from here we can calculate the ratio of the viscosity. So we cannot calculate the absolute value of the viscosity because we do not know this constant. This constant is different. The constant here in the equation is different for the two cases. For the case of the less than 30 kilogram of higher than 30 kilogram per mole, this constant is also different. So here now let's look at how to calculate the ratio between the different cases. For example, here we have A, 12 kilogram per mole at 200 degrees. B, the same molecular weight, 150 degrees. C, higher molecular weight, higher temperature. And we want to calculate the ratio between the A and the B. So what you can do? You can do the log. But here we have the log, right? But here we have the log. We can do something like this. We have the mu A minus. So this is what you can calculate. So in this case, it is 12 kilogram. It is the n equal to 1. So n equal to 1, or equal to log. Sorry. So this term here will cancel out because they are both 12 kilogram per mole. So this term will cancel out. So you only have this temperature curve. So you can guess this one. This one is equal to, as you know. Yeah. This way you can figure out the ratio between mu A and mu B. So now let's look at how to get the ratio between mu B and mu C. So B and C. So B is 12 kilogram per mole, 150 degrees. C is 120 degree, 120 kilogram per mole, 200 degrees. So the trouble is, so they have different. So here 12, here is 120. So this one is smaller than 30 kilogram per mole. This one is higher than 30 kilogram per mole. So this one, you see the n number is different. So if you draw it, it's something like this. So here is the molecular weight. So this is the 30 kilogram per mole. 30 kilogram per mole. Here is the viscosity. So when it is below 30, it is something like this, small slope. When it is above 30, it becomes big slope. So this is 30 kilogram per mole. So now we have one is on the right side, it's here. Another one is 12, is on the left side, it's here, so it is here. So how to get the ratio between here and here? So this is not obvious. So if you compare them directly, you get the trouble because they are on the two sides. So what you can do, so you compare this one with 30 kilogram per mole, and you compare this one also with 30 kilogram per mole. And this way, you can get the ratio between this one and this one. So that means, what do? You do this one. mu B over mu 30. This one it can be on the left side. You can see 30 minus. The 30 minus is on the n equal to 1. So times 30 plus over mu on the right side is 120 mu C. You can calculate this way. This one is on the right side 30 kilogram per mole. This one is also on the right side, so n equal to 3.4. You can get this. You can get this ratio. Then this term here and this term here, they will cancel out. This is why you see 30 plus 30 minus is like a 30 kilogram per mole. It's very close, infinitely close. This way you can find out the ratio between mu B and mu C. So you will do some calculation problem using this formula here. So thank you.